All right, let's dive into another deep dive. Today we've got something that's going to make you think twice about data. Simpson's paradox.
Ooh, yeah.
It's this statistical phenomenon where a trend can be there, clear as day in different groups of data, but then poof, vanishes or flips completely when you lump all the data together.
It's wild, right? What's so interesting about Simpson's paradox is that it really shows how easy it is to get tricked by statistics if you don't, look
Mm,
under the hood.
exactly. It's
Mm,
not just the numbers themselves, but the whole cause and effect dance going on between those variables.
absolutely.
And for this deep dive, we're turning to the Stanford Encyclopedia Philosophy's entry on Simpson's paradox. And trust me, it's a real mind bender.
Hmm.
Ever had that feeling that you can twist statistics to tell whatever story you want? Well, get ready to have those suspicions validated because Simpson's paradox throws a huge curveball when it comes to making sense of data.
Oh, it's like a statistical illusion, kind of like one of those magic tricks where what you see at first glance isn't the whole picture at all. And as we're going to see, this illusion has some pretty big implications for how we understand cause and effect, especially in things like medicine, social science, even evolution.
Speaking of illusions, let's start with a classic example, one that's often used to show this paradox in action. Imagine you're looking at data for a new medical treatment.
Okay.
In separate groups, like men and women, the treatment seems to be working. More people are getting better in each group when compared to those who didn't get the treatment. But here's the catch. When you combine the data for men and women all together, suddenly the treatment looks ineffective, or maybe even harmful.
Yeah, this is where it gets really interesting. This source kind of explains this head scratcher by saying there's probably another variable lurking in the shadows, something messing with the results that we don't see right away.
Right, like a secret ingredient.
Exactly. This hidden variable is often called a confounding variable. In our medical example, it could be anything like age, lifestyle choices, maybe even access to healthcare.
Ah, I see. So even if it seems like the treatment is doing its job in each group, there might be these other sneaky factors that are actually driving those recovery rates.
Right.
And then when you throw all the data together, those factors become more obvious and kind of hide the apparent effect of the treatment.
Exactly. The Stanford Encyclopedia, it uses this idea of a weighted average to explain it.
Okay.
Think about it like this. If you have two groups, each with their own average scores, and one group is way bigger than the other, well, the combined average is going to be pulled more towards the bigger group, even if the smaller group had a totally different average. This weighting thing, it can really distort the picture and lead to that paradoxical reversal we see in Simpson's paradox.
Okay, so it's not as simple as just the raw numbers. It's about the proportions,
Hmm.
and how these different variables are all connected to each other.
Absolutely. And that takes us to the real heart of the matter here, causality. Simpson's paradox really forces us to think long and hard about how we figure out cause and effect relationships. It challenges this classic idea that if a cause is there, it should always make its effect more likely.
Right, because in these paradoxical cases, we see that a cause might seem to have a positive effect in separate groups, but then when you look at the big picture, it has a negative effect, or the other way around. So how do we even begin to make sense of this?
Well, the source points to the work of this philosopher, Nancy Cartwright. She says we have to consider the background context when we're looking at these cause and effect relationships. Basically, a cause might only work under certain specific conditions, and those conditions can change depending on other things that are present.
So it's like saying that watering a plant will help it grow, but if it's already drowning in a pot full of water, that water is going to hurt it, not help it. The
Exactly.
context, it really matters.
Yeah, Cartwright emphasizes this idea that causes don't work in a vacuum. They're all tangled up with a bunch of other causes and conditions, and those background factors can have a big impact on what happens in the end. Simpson's paradox is a big flashing sign reminding us that we can't just assume there's this straight line between a cause and its effect.
This is getting pretty deep. It's like Simpson's paradox is taking us on a philosophical adventure, making us question the way we think about how the world works.
Oh, it definitely challenges our intuition about cause and effect, that's for sure. And it really highlights how important it is to be careful and think critically when we're trying to make sense of data.
Okay, so we've got this theoretical framework now for understanding Simpson's paradox, but I'm really curious about how this all plays out in real life.
Yeah.
What are some real-world examples of this paradox in action?
Oh, let's dive into some specific examples then. One that really jumped out at me from the Stanford Encyclopedia was about standardized testing, like SAT scores here in the US.
Oh, okay.
There was this time when average SAT scores were going up, which sounds like a good thing, right?
Yeah.
But here's the paradox. When researchers looked at the scores of students who all had the same GPA, the scores were actually going down for each GPA group.
Wait, what? How is that even possible? If the overall average is going up, shouldn't the scores for each GPA group be going up too?
You'd think so, right? But this is classic Simpson's paradox at work.
Wow.
The likely culprit here was grade inflation. As grades got easier to come by, the group of students with a certain GPA, they weren't as strong academically on average, even if the overall average SAT score was going up.
So even though it looked like students were doing better overall, the real trend, the one hidden underneath, was actually showing the opposite direction for individual GPA groups.
Exactly. And it shows you just how risky it is to rely on this big picture data without looking at the specific subgroups and those potential confounding factors. In this case, grade inflation was that sneaky variable that hid the real trend within the GPA groups.
Okay, that's a pretty clear example of how Simpson's paradox can really lead you down the wrong path if you don't take a good, hard look at the data. But let's dig into another real-world situation, something a bit more, well, controversial. The Stanford Encyclopedia mentions this famous case involving admissions data from UC Berkeley.
Ah, yes, the Berkeley admissions case. This one really stirred up a lot of debate about gender bias in higher education.
I can imagine.
At first glance, it seemed like men were more likely to get accepted into grad programs than women, which seemed like there might be some discrimination going on. But when researchers dug deeper and analyzed the acceptance rates for each department separately, they couldn't find any evidence of bias against women.
Wait, hold on. So how could there be bias in the overall data, but no bias when you look at each department?
Oh.
That sounds like Simpson's paradox striking again.
Exactly. What they found was that women were more likely to apply to departments that had lower acceptance rates overall, and that skewed the big picture data, making it look like women were getting the short end of the stick. This is a perfect example of how Simpson's paradox can pop up in sensitive areas like social justice and equality.
Yeah.
It raises these really crucial questions about how we interpret data and how we can accidentally jump to conclusions about bias.
So in this case, the department's acceptance rate was the confounding variable, which you wouldn't have noticed if you just looked at the overall data. This really shows how important it is to break down the data into smaller groups and figure out the specific pathways involved.
Absolutely. In the Berkeley case, looking at the choices that people made when they applied to different departments was key to understanding why the overall data painted such a misleading picture.
This is getting really thought-provoking. Simpson's paradox is like a statistical detective story, where we have to hunt for clues and put the pieces together before we can make any judgments.
It really is. It's not just about crunching numbers. It's about understanding the story behind the numbers, and all those complex factors that can create the patterns we see.
It's like a reminder that data doesn't always tell the whole story on its own. We need to be the interpreters, the detectives, to dig beneath the surface and find the real truth.
And that's a skill that's becoming so important in our world today. We're drowning in data, statistics, and graphs everywhere we look.
It's overwhelming.
It is, and it's up to us to develop those critical thinking skills so we can navigate this information overload.
Absolutely. Simpson's paradox is this powerful reminder that statistics can be super misleading, and we need to be aware of those potential traps. But it's also an invitation to think deeper, to ask more questions, and to approach data with a healthy dose of skepticism and curiosity.
That's such a great point. While Simpson's paradox might make you want to distrust statistics altogether, it's actually a call to engage with them more thoughtfully, to be more careful about what we believe.
Yeah, to be more discerning consumer of information,
Yeah.
right?
Exactly.
I completely agree. Well, we've covered a lot of ground in this first part of our deep dive into Simpson's paradox. We've talked about the basic idea, dug into some real-world examples, and started unpacking the philosophical side of things. But there's still a lot more to explore.
There is. In the next part, we're going to go even deeper into the philosophical debates around Simpson's paradox, see how it affects decision-making, and even venture into evolutionary biology to see how this seemingly simple statistical quirk can shed light on some of nature's most puzzling mysteries.
So buckle up, listeners, and get ready for an even deeper dive into the fascinating world of Simpson's paradox. We'll be back soon to unravel more statistical mysteries and challenge your assumptions about how the world works. Stay curious. Welcome back to our deep dive on Simpson's paradox. We've already seen how this statistical phenomenon can really turn our ideas about data on their head, but now let's get into some of the deeper philosophical and practical stuff.
Yeah, for sure.
In the first part, we talked about how Simpson's paradox challenges our understanding of cause and effect. So now let's think about how those challenges play out when we're making decisions.
Yeah.
If something looks helpful in separate groups but harmful overall, or the other way around, how do we even decide what to do?
Right, that's a great question. It's like Simpson's paradox throws a wrench in all those traditional decision-making models, especially the ones that are based on maximizing expected utility.
Absolutely. One of the fundamental ideas in decision theory is this thing called the sure thing principle. It basically says that if you prefer option A over option B in every possible scenario, you should always go with A no matter what actually happens.
Right.
Okay, that makes sense, right? If A is always better than B, why would you ever choose B?
Exactly. But then Simpson's paradox comes in and throws a curveball. It shows that our preferences, based on those subgroups, they might not actually line up with our overall preferences when we look at the combined data.
So even if you would pick A over B in every single group, when you look at all the data together, it might look like B is actually the better choice.
Yeah, that's the dilemma. The Stanford Encyclopedia entry talks about the work of this statistician, Colin Blythe, who argued that Simpson's paradox basically limits the scope of that sure thing principle. It forces us to stop and think, should we base our decisions on those patterns we see in the subgroups or on the overall data?
Wow, I can see how that would lead to some pretty heated debates. Which perspective should we prioritize? Is there even a right answer?
There isn't really an easy answer. It depends on the specifics of each situation and those cause and effect relationships we've been talking about. But Simpson's paradox definitely shows how important it is to be careful and to understand that there might be conflicting evidence out there.
It's like we need to become data detectives, right?
Right.
Not just reading statistics, but actually investigating the underlying causes and relationships.
I like that. We need to be asking the tough questions like, what could those confounding variables be? Are there other explanations for the trends we see? Are we even looking at the right level of analysis?
Right. And to make things even more complicated, there are different interpretations of what's actually paradoxical about Simpson's paradox.
Oh, yeah, definitely. The Stanford Encyclopedia talks about this fascinating viewpoint from Judea Pearl, a really well-known computer scientist and philosopher who's all about causality. He argues that the paradox actually comes from mixing up probabilistic reasoning and causal reasoning.
So in other words, we tend to confuse observations about correlations with statements about cause and effect. We see a trend in the data, and we automatically assume it means there's a cause and effect relationship, but that might not be true at all.
Exactly. Pearl argues that if we can clearly separate correlation from causation, the paradox disappears. He proposes what he calls a causal sure thing principle, which basically says that if an action makes an event more likely in every single subpopulation and it doesn't change how those subpopulations are distributed, then it must also make that event more likely overall.
So this causal interpretation is saying we need to go beyond just seeing patterns in the data. We need to really understand the underlying causal mechanisms that are at work.
That's the main takeaway here. It's not enough to just say that A is correlated with B. We have to understand why and how A might actually be causing B.
This is fascinating. So we have these different interpretations of Simpson's paradox, and they each offer a unique perspective on how to solve those apparent contradictions it presents.
Hmm.
But are all the experts on board with Pearl's causal explanation?
Well, not necessarily. The Stanford Encyclopedia mentions that there's still a lot of debate about the nature of the paradox. Some people argue that it can be explained purely through math or probabilistic reasoning without bringing in the idea of causality.
So there's still this ongoing discussion about what's at the heart of Simpson's paradox. Is it a problem of causality, probability, or something else entirely?
Exactly. And that's what makes this topic so intellectually stimulating. It makes us question all those assumptions we have about how we interpret data, the nature of cause and effect, and the limits of our intuition.
We started with this seemingly simple statistical quirk, and now we're grappling with some of the most fundamental questions in philosophy and science. It's pretty amazing.
I know, right? It's amazing how one concept can open up so many avenues of inquiry. And it really shows the power of interdisciplinary thinking, bringing together ideas from statistics, philosophy, and computer science to tackle these really complex issues.
Well, we've covered a lot of ground exploring the philosophical and decision-making aspects of Simpson's paradox. But you mentioned earlier that this paradox also shows up in the field of evolutionary biology. Now, that's something I've got to hear more about. How can a statistical concept be relevant to the study of evolution?
Oh, that's a great question. It takes us to one of the most fascinating applications of Simpson's paradox. And it all has to do with the units of selection debate in evolutionary biology.
Okay, tell me more about that. What is the units of selection debate all about?
It basically revolves around the question of whether natural selection works mainly at the level of the individual or whether selection at the group level can also play a significant role.
So is it all about survival of the faced individual, as we always hear? Or can groups with certain traits also have an evolutionary advantage?
That's the big question. And Simpson's paradox comes into play when we think about the evolution of altruism.
Altruism, the act of helping others even when it costs you something? That seems like it goes against the idea of individual fitness, right? If natural selection favors those who are best at surviving and reproducing, how could altruism ever evolve?
That's where group level selection comes in. Imagine you have a group of animals, and some individuals are altruistic, meaning they sacrifice their own well being for the benefit of the whole group. Within each group, those selfish individuals might be fitter, but
And here comes the paradox.
exactly. If groups with more altruists are more successful overall, then altruism could still spread through the population, even if it's a disadvantage at the individual level.
So it's like those altruistic individuals are taking one for the team, but their sacrifice ultimately helps the whole group succeed in the long run.
Yeah, that's a great way to put it. And it shows how Simpson's paradox can help us understand those seemingly paradoxical phenomena in nature. It shows how different levels of analysis can lead to different conclusions and how important it is to consider the interplay between individual and group dynamics.
This is mind-blowing stuff. It's amazing how a statistical concept can help us understand such complex biological processes.
And it doesn't stop there. Simpson's paradox has even sparked a meta-debate about whether natural selection itself should be seen as a causal process or a statistical process.
Hold on, are we now questioning whether natural selection is a cause or just a statistical description of what happens in nature?
Yep, that's right. Some people argue that Simpson's paradox shows that natural selection is just a statistical thing without any real causal power.
But others say that the paradox actually supports a causal interpretation of natural selection. Wow, this is getting deep into the philosophy of science.
It is. And it just goes to show how Simpson's paradox has implications that go way beyond statistics. It reaches into fundamental questions about the nature of causality and the processes that shape life itself.
This deep dive has really taken us to some unexpected places. We've explored the mathematical and philosophical sides of Simpson's paradox, its impact on decision-making and policy, its role in sensitive social issues, and even its connections to evolutionary biology. I have to say, this is one of the most thought-provoking episodes we've ever done. All right, welcome back to the final part of our deep dive into Simpson's paradox. We've explored the mathematical quirks, the philosophical rabbit holes, and even how it pops up in evolution. But now let's bring it all back down to earth. Back to us regular folks trying to make sense of the world.
That's so important. I mean, we're swimming in data and statistics every single day. From news headlines to scientific studies to those ads that seem to follow us everywhere. Simpson's paradox really shows how important it is to be critical of all that information, to not just swallow it whole.
Totally. It's like we need to develop this statistical spidey sense, right? To be on the lookout for those hidden variables and tricky trends that can trip us up.
I like that, a statistical spidey sense. So how do we become these savvy data detectives?
Well, we've talked about some key strategies throughout this whole deep dive. I think the first thing is asking the right questions. Where did this data come from? Who gathered it? And what was their purpose? How did they analyze it? What are those sneaky confounding variables that might be skewing the results?
Those are all such good questions. We need to go beyond those attention-grabbing headlines and really dig into the methods and the context. Don't just accept a statistic or a graph at face value, without understanding the story behind it.
Right, and like we've seen, it's so important to think about bias. Bias in the data itself, but also in how we interpret it. We tend to see what we want to see, especially when it confirms what we already believe.
Oh yeah, confirmation bias is a real thing. But we can fight back by being open to different perspectives and actively looking for evidence that might challenge our assumptions.
It's all about having some intellectual humility, right? Admitting that we don't have all the answers and being willing to change our minds when we see convincing evidence, even if it contradicts what we thought before.
That's the sign of a true critical thinker, someone who's open to new information and ready to adjust their views based on the evidence.
So in a way, Simpson's paradox is actually a gift. It's like this wake-up call reminding us that The world is way more complex and nuanced than it seems on the surface.
Absolutely. It's a reminder that we can't just blindly trust the numbers. We need to be engaged, you know? We need to be critical thinkers who are willing to question, dig deeper, and really search for that complete understanding of the data.
We can't just be data dummies. We got to be data detectives.
I love that. And remember, even the experts can get tricked by Simpson's paradox. It's not a weakness to admit that we don't have all the answers, but it is a strength to be open to learning and updating our understanding.
So listeners, the next time you see a statistic that seems too good to be true, or a trend that just doesn't feel right in your gut, remember Simpson's paradox. It might be the key to unlocking a deeper, more accurate understanding of what's really going on.
That's right. Keep asking questions, keep exploring, and never lose that curiosity about the world around you. The data is out there, just waiting to be interrogated. And with a critical eye and a curious mind, you can find the truth hiding beneath the surface.
And that's the beauty of a good deep dive. It's all about going beyond the surface, challenging our assumptions, and really embracing the complexity of the world. So until next time, keep those brain cells buzzing, and remember, there's always more to discover.